Good evening to all of you. We welcome you all to the fifth IEEE Let's Talk session for this year, BSc to PhD, Machine Learning with Physics. Let's Talk is a series of sessions organized by the IEEE Young Professionals Sri Lanka to educate young professionals on timely matters and non-technical skills that are required to shape up their careers. Our guest speaker for today is Mr. Tharindu Jayasinghe, who is a PhD candidate from the Ohio State University. Let me give you a small introduction about our guest speaker today. He is a graduate research associate in the Department of Astronomy at the Ohio State University, USA, affiliated with the Center for Cosmology and Astroparticle Physics. Growing up in Sri Lanka, he completed his studies at the Lyceum International School in Nugegoda, received his BSc degree in physics from the California State Polytechnic University, Pomona, USA in 2017 and his MSc degree in astronomy from the Ohio State University, USA in 2020. He is currently a PhD candidate in the Department of Astronomy. He was a valedictorian for the Cal Poly Pomona College of Science, class of 2017, and was a recipient of the Julian A. McPhee Outstanding Student Scholar Award in 2017. He was awarded the Chambliss Astronomy Achievement Student Award by the American Astronomical Society in 2019 for his exemplary research. He is a team member of the All-Sky Automated Survey, the Supernova. His current research interests include time domain astronomy, stellar astrophysics, variable stars, and compact object binaries. His speech will highlight his research work and his experience on his life as a PhD candidate going from a BSc student, which will be insightful for all of us as students who are pursuing their higher studies. Before we begin, let me give you a small heads up on how we will be conducting the Q&A session. In each confirmation email sent to all the participants contains a link to submit any questions you have. The same link will be posted in the chat window as well of this meeting. And if you have any questions, you may submit them in that given link and they will be asked at the end of the speech and there will be a Q&A session conducted. So without any further delay, let's start the session. Mr. Tharindu Jayasinghe, over to you.
Thank you so much for the lovely introduction. Hi, everyone. I'm Tharindu Jayasinghe, and today I will be briefly talking to you about my work with the All-Sky Automated Survey for Supernovae. My talk is titled A Data-Driven Approach to the Variable Universe Through the All-Sky Automated Survey for Supernovae, and I will begin my talk right now. Oh, okay. So, briefly outlining my talk, I will briefly give you an introduction about myself, and I'll move on to an explanation of how to approach a career in astronomy. And I will move on and talk about the All-Sky Automated Survey for Supernovae. And finally, I will talk about my research with the discovery and characterization of variable stars with Assassin. And then we will take questions. So about myself, as they mentioned, I'm a PhD candidate at the Department of Astronomy at the Ohio State University. I work with 3 advisors there, and I'm a team member of this All-Sky Automated Survey for Supernovae, which I will talk to you about in a little more. So regarding my education, I first started off at the Lyceum International School in Nugegoda, and then I did a dip program at the American National College, or ANC, in Colombo, and I transferred to Cal Poly Pomona to complete my BSc in physics. And currently at the Ohio State University, I finished my master's this year, and I'm expected to finish my PhD in a couple more years. So without further ado, let's talk about astronomy. What is astronomy? So if you Google the term astronomy, Merriam-Webster basically defines it as the study of objects and matter outside the Earth's atmosphere and of their physical and chemical properties. I'm sure all of you have seen these beautiful images taken by a variety of space telescopes. So you have stars and galaxies. But you might wonder, how do I become an astronomer? So in the first part of this talk, I will talk to you about a career in astronomy and how I came to where I am right now. So let's start with the undergraduate or the bachelor's foundation for a path in astronomy. An astronomy program basically requires a very solid foundation in physics, mathematics, and computer science. So the physics requirements basically cover a wide variety of things. You need to know about electricity and magnetism, atomic and nuclear physics, thermodynamics, statistical mechanics, and quantum theory, of course. And a little known fact is that programming is extremely essential to approach this field. So the most popular languages that are used in this field include Python, C++, and surprisingly Fortran from a few decades ago. So to approach the next stage or the graduate stage, one critical and requirement is supervised research experience. That is basically following a research project and getting some results. And I would say we as Sri Lankans have a very good foundation in physics and programming. And in our schools, we learn a lot about math, and we have a strong foundation there. But the only thing that limits us in this field is basically the supervised research experience. And that is basically held back by the lack of investment in astronomy in the current country. So we don't have a modern national observatory, but if we did, I have no doubt that a lot of Sri Lankans can actually like approach this field and do a lot of great things. So what about graduate studies? So most astronomy positions require a PhD, and these PhDs take roughly 5 to 6 years of graduate work. And in the US definition of a PhD program, basically you do classes for the first 2 years, and then you get a master's degree on the way to your PhD. And the most important requirement of a PhD is the independent studies and research. And to do this, you find a problem in the field and you work on solving it. So you basically develop critical thinking skills and you analyze data. So there's a lot going on in a PhD. And in the current climate, PhDs are very competitive and they require a B average or higher for admission. But another very good fact about these programs is that they are fully funded. The universities basically pay your tuition, and they also give you a stipend, money to basically cover your living expenses and food costs and etc. So PhD programs in astronomy and astrophysics are basically concentrated in the USA, Canada, Europe, mostly Germany and the UK, and Australia. And I know of a few Sri Lankans who are doing these kind of programs, especially in Australia. So again, don't be limited by this. Sri Lankans can totally do this. We have the skills and necessary aptitude to approach cutting edge research in astronomy. So this is a word cloud that was generated for the graduate students in my program, which shows the kinds of things that they study in the field. So you can see there's a lot of variety. Astronomy is a really huge field with a lot of things to do. And the things we know about, like galaxies, stars, are very popular. But then the cutting edge things like gravitational waves are much more popular in the modern day than a few years ago. So there's a lot of things to do. And a very, I would say, a very popular field right now is the study of exoplanets, trying to find planets around other stars. So if you are interested in that, this is a good time to approach the field. And I will talk a little bit about my journey, like what I did to come to where I am right now. So when I was at Lyceum, I did my Cambridge advanced level examinations in computer studies, physics, mathematics, and further maths. As I said, these courses really provided me the background to approach a major like this. And since I did computer studies, I developed a lot of programming skills early on. And again, I know that a lot of you are very, very good at programming, and this is very important. because there's a lot of data analysis that you need to do. And to do that, you need to have very good programming skills. And then I did 2 years at the American National College, or ANC, where I basically did a few general education courses, because it is cost effective to do the general courses in Sri Lanka. And then I transferred to Cal Poly Pomona in the United States after 2 years to finish my degree. What did I do in the United States? So at Cal Poly Pomona, I was a physics major. I did a physics bachelor's degree. And as I mentioned before, I took a lot of advanced physics and astrophysics courses there. And I did undergraduate research. This is very important because you need to have research experience before you apply to a PhD program. And I did this kind of research for over 1.5 years. And over the course of this, I developed an interest in stellar astrophysics. That is basically the study of stars. And I applied to 10 graduate programs in the United States. And as I said before, it's very competitive. And the acceptances basically depend on if you have a match with an advisor in the prospective university. And I was accepted to 3 programs at the Ohio State University, the Penn State University, and the University of Arizona. In the end, I decided to go to the Ohio State University. So this is what I'm doing right now. I completed my coursework in the first 2 years. We basically did a lot of astrophysics courses in the first 2 years. And then in the 3rd year, there's something called a PhD candidacy exam, where you basically have to defend your work that you've been doing so far. And at this point, you earn your master's degree. And in the next couple of years, you basically do dissertation research to get your PhD. And that includes writing papers and observing proposals to get time from observatories to make observations. So currently, I'm a first author of 9 peer-reviewed papers, and I'm a co-author on 8 others. So that is basically my journey so far, and I'm continuing my work, and I'm expected to do my PhD, earn my PhD in a couple of years. And now I will talk to you about the research that I work on. In particular, I will start with the All-Sky Automated Survey for Supernovae, or ASSASSIN. I will refer to it as ASSASSIN because it sounds cooler and it's shorter. So moving on. In the modern day, it'll be very hard to believe that only human eyes basically monitor the entire sky every night. There isn't an optical survey. There isn't an optical survey that frequently monitors the entire sky. But we are changing this with the All-Sky Automated Survey for Supernovae, or ASSASSIN, where we monitor the entire visible sky every night. And to put things into context, the sky is really big. How big is the sky? So if you were to calculate this, there are basically 41,250 square degrees across the entire sky. And if we were to take an image of the entire sky at very high resolution, that would be basically almost 500 gigapixels, amounting to roughly 1 terabyte for an image, a single image of the entire sky. So this is a field that generates a lot of volume, especially if you want to monitor the entire sky all the time. So what is ASSASSIN? ASSASSIN is a survey that monitors the entire sky every night in real time. And we do this in optical wavelengths, and we use commercially available telephoto lenses and CCDs to build our devices. And the primary goal of this project was to find supernovae and other transients in the local universe. And we want to announce these discoveries publicly so people can follow things up and get data. So this image on the right is an example of an ASSASSIN telescope. You see 4 telephoto lenses. These are Nikon lenses that we implement into the telescope. And an interesting fact is how we monitor the stars. So here I've shown the transmission curves for a bunch of different filters. So we use filters on our lenses to limit the light that we get into a certain part of the wavelengths. Here in Assassin, we monitored the sky in the G band, and uh, I've drawn two lines in green to denote the wavelength range that our human eyes is sensitive to. So we can basically see everything from 380 nanometers to 700 nanometers, and that is defined as the optical wavelength range. And Assassin monitors the stars in a limited range in the optical limit. So moving on, a little more about Assassin. So each Assassin unit has 4 cameras, and we have 5 of these units all over the world. And these lenses are very small. They are 14 centimeter lenses, and they're connected to a CCD, which is actually the most expensive part of this project. To buy the CCDs, we need to have good CCDs to actually see faint stars. But surprisingly, the commercially available lenses that we get from Nikon are very good for the work that we do. And we monitor roughly 100 million stars every night. And we take 6,000 different images through our network. And we monitor 40,000 square degrees every night. And in this map, I've shown the current locations of the Assassin survey. So we have a telescope in Hawaii, in Texas, and 2 telescopes in Chile, 1 in South Africa, and we are bringing 1 online in China right now. So there are telescopes all over the world, and we need this basically if we want to achieve our goal of monitoring the entire sky. We need to have redundancy, and we need to see the sky from both the northern and southern hemisphere. So on the right, we have an Assassin collaborator here holding one of these lenses. So these are lenses you can, as I said before, you can buy this commercially, and folks use this in their DSLRs, but they can also be adapted to astronomy research. And this is particularly enticing because they're so much more cheaper than building dedicated lenses, which cost millions of dollars. So a lens like this is basically $3,000 to $4,000, which is considerably cheaper if you think about having multiple telescopes all over the world. So here I've shown the Assassin field of view. So each camera has a CCD, and there are 4 cameras per unit. So there's some overlap between the cameras, as you can see here. And the field of view of a single camera is basically 4.5 degrees. And to put that into context, I've shown the moon here, which is roughly half a degree, tiny. And the Assassin field of view is quite large compared to the size of the moon that we see. So this allows us to scan a large part of the sky very efficiently. And here I've shown the sky coverage map for Assassin. So this is basically the entire sky. And these are the Assassin fields that you can see annotated here. And they're colored by how many times they have been observed over the years. So some parts of the sky have been observed over 4,000 times. And we've been observing the sky since 2014. And since this time, we have a data set of roughly a petabyte. So this is a lot of data. And I'll get to this later. Big data in astronomy is a very important consideration. And as I said before, you need to have very good programming skills and machine learning skills, in fact, to analyze this huge set of data. So Assassin is a global project. We have people from all over the world contributing to our survey. And we also have a lot of amateur astronomers who participate in the survey. But you might be interested, how do we do this? So the answer to that question is a lot of image processing. And a tool that we use, which is particularly awesome, is called image subtraction. And I will illustrate what this is in a few moments. So to put things into context, this is the Large Magellanic Cloud, which is located roughly 158,000 light years away from us. And it's a dwarf galaxy that's a companion to the Milky Way. So this is what it looks like in multiple filters. You can have color. So it's a really beautiful dwarf galaxy. And this is what it looks like in Assassin. So here I've shown what is called a reference image. A reference image is basically built by adding together the data that we take over, let's say, a year or so, and averaging things out. So we have understanding of the average brightness of the stars in that image. So it's a reference that we use for what we call image subtraction. And every night we get a new image. So this is something that we can get every day. And we have the reference image that we have built up over many years. So what we do is we subtract the reference image from the new data that we get to see what changes from today to what we had before. That tells us information about, oh, did a star suddenly increase in its brightness, or did it suddenly go dimmer? That gives us a lot of information, and it's a very powerful tool. So once you subtract the data, this is what you see. So it looks kind of boring at first, and I want you to focus on some of these spots and speckles. So you have the spots in white and black, and these show sources that change in brightness. Either they become dimmer or they become brighter compared to the reference image. And this is the entire purpose of the Assassin survey, to find stars that change in brightness over time. And the biggest reason that the survey started was to find transients like supernovae in the local universe. So based on the image subtraction pipeline, you get a few million targets where something changed. And these are largely dominated by false positives. So we have implemented many machine learning classifiers, including convolutional neural networks, to basically cut out the number of false positives. And after these cuts are made, there are roughly 200 to 500 candidates that are left. And then the Assassin collaborators, what we do is we scan them by eye. So there's human verification of these transient events. And following this, we identify interesting transients that probably could be supernovae. And then what we do is, to make sure that they are real, we follow these up with other telescopes. And this is done in the course of a few hours after we get new data. So we use a wide variety of telescopes all over the world to follow up our candidate transients and to make sure that they're real. So that's a lot of interesting things that go behind the scenes to identify supernovae. And as a summary of what Assassin has been able to accomplish over the years, we have discovered over 1,000 supernovae since 2014. So supernovae are very rare. And the reason that we want to find these is to study the expansion of the universe, to identify what happens when stars explode. There's a lot of interesting things that you can do. And we also identified 220,000 new variable stars, which I will talk to you very soon. And in addition to this, there's a lot of other interesting things that we find because we monitor the entire sky every night. There are like stars that have flares, huge flares that we see in our data. Then you have galaxies with outbursts, tidal disruption events where stars are stripped apart by black holes. And we also have comets. We identified 2 comets so far. And interestingly, last year, Assassin was able to identify a killer asteroid. And it was kind of cool because people had not spotted it before. And we were able to send this data to NASA, and it was cool. But fortunately, there's no risk of this asteroid hitting us, so you don't have to worry about that. And before I talk to you more about my research on variable stars, I want to talk to you a little bit about big data in time domain astronomy. So what Assassin does can be basically classified as time domain astronomy, because we take data of the entire sky every night and we have time series data for a bunch of stars. And this kind of astronomy has become very popular in the modern day, particularly because gravitational waves have been discovered starting 2015. And people want to follow up gravitational wave events to see if there's an optical counterpart to it. So people have built up many different surveys to monitor the sky to find supernovae, and Assassin is one of them. But Assassin is the only survey that monitors the sky from both the northern and southern hemisphere. Um, because again, it's cost limited. If you want to have a telescope in Chile, it's kind of expensive. But given that Assassin uses very cost-effective lenses and CCDs, we can do this. But the important point is that the data volume in this field is rapidly increasing from terabytes to petabytes. And as you can imagine, this requires a lot of analysis. And the best way to do that is machine learning. And if you know machine learning, it's a really good time to join the field, because machine learning techniques are very important right now at interpreting and analyzing this huge volume of data. There's no way that a single human can go through petabytes of data. So you need a computer to analyze the data for you. Um, to put things into context a little more, Assassin has, as I said, a petabyte of archival data, and we generate a few hundreds of gigabytes every night. A competing survey called the ZTF survey, they generate roughly 1.5 terabytes every night. And as you can see, this will add up to petabytes over a course of a few years. But in a few years, you have this telescope called the Large Synoptic Size Survey, the LSST telescope. And I've shown an example, a computer-generated picture of the telescope here. It's still under construction, but this is expected to generate 20 terabytes of data every night. And even before the telescope is built, people are working on developing machine learning techniques at identifying supernovae and other interesting candidate events from this huge set of data. So one interesting application of time domain astronomy is the follow-up to gravitational wave events. So here I've shown the LIGO waveforms for a neutron star merger that was identified in 2017. So the area you need to focus on is this nice curve here where you can see gravitational wave in the data from the LIGO collaboration. And this was due to a merger of two neutron stars in a very distant galaxy. But the reason why this event was game-changing, because LIGO had been monitoring the sky from 2015, and they've identified black hole mergers, but black holes don't produce any light. So we don't see any evidence of this merger other than in the gravitational waveforms that LIGO gets. But neutron stars are different, and they basically can have an optical counterpart or light being produced during the merger. And this is exactly what people found. So here in the top right image, you can see a small source right on top of this galaxy in the middle. And this is the optical counterpart to the gravitational wave event that LIGO identified. And people had never identified something like this before. And as you can imagine, it was groundbreaking. So the image on the left on this two-panel figure shows the data after a day or so after the merger happened. And after 14 days, the source is not there in the data anymore. So this basically falls under time domain astronomy. You see a source coming on for a few days, and then it disappears. And surveys like Assassin will help us identify these optical counterparts to gravitational wave events. So there's a lot of interest in this field right now. All right. So the next part of this talk, is where I will talk to you about my work on the study of variable stars using assassin data. Let's start with a brief history on this topic. So I will start with the definition of a variable star. Variable stars are stars whose brightness changes over time. And this field has a very, very interesting history. People have been monitoring the sky for thousands of years. The sky is accessible to everyone, regardless of where you are on the earth. So people look up to the sky because stars are beautiful. And a few thousand years ago, you didn't have light pollution and all that nonsense. So you can see the entire Milky Way with your own eyes. And during this process, ancient human beings, they discovered that some stars, their brightness changes over the course of days or years. And at that point, they had no idea what this was. And however, they integrated this knowledge into their culture. For example, Aboriginal Australians, they noted that red giant stars, their brightnesses changed over time. And they kind of implemented this as a sign of war. So there were a lot of interesting things that people used to do with the stars. And ancient Egyptians actually discovered that a star had a period. So basically, they noted that the brightness of a star called Algol basically changed over the matter of few days. And they identified that, okay, this actually changes over, let's say, 3 days. Every 3 days, the star will change in brightness. And it's kind of remarkable that ancient human beings were able to do that. So this is a few thousand years back. And in the modern astronomy, Johannes Holwerda, he was the one who actually first discovered that, oh, there's something interesting about stars that vary. And he discovered a star called Omicron Ceti, or Myra, in 1638. So it's basically a star like the GIF I've shown here. It's a red giant that expands and contracts over the matter of 300 days or so. And in 1786, there were 12 variable stars known. But by 2018, people have discovered over 1 million of these objects. So yeah, things have really exploded because of the availability of big data, machine learning, and so forth. Okay, so a little more about stellar variability. If you think about how many stars there are in the Milky Way, there are roughly 250 to 500 billion stars in our galaxy. And the best observatories that we have right now can observe maybe a few billion of these. And Assassin, because we use small telescopes, we can't see everything. We can only see the brightest stars. And that limits us to roughly 100 million stars in the Milky Way. And of these stars, only a few % of them are variable. So variable stars are very rare. But given the rarity, they are actually very powerful astrophysical tools. For example, variable stars can be used as distance indicators through the galaxy. Surprisingly, the distances that we can get to stars is very hard to achieve. And having variable stars as distance indicators have basically changed the field of astronomy. And a fun fact is that through the study of variable stars, Edwin Hubble was first able to identify that there were external galaxies and that the universe was expanding. So again, thanks to variable stars. And variable stars can also be used to study the stars in binary systems in exquisite detail. And we can get the measurements of the sizes and the masses of the stars through such systems. And a recent tool that's been used through variable stars is to actually study the structure of the Milky Way. And this is also accomplished through the variable stars that people identify. And as I mentioned before, the field has been revolutionized in the modern era because of CCDs and large-scale wide field surveys. We are able to monitor large parts of the sky over many, many, many years and see, oh, these stars vary. But why do stars vary? That's an interesting question. So the reasons can be divided into two main categories, which basically are the intrinsic variables and the extrinsic variables. So intrinsic variability happens because stars change in their properties over time. As stars evolve and as they approach their death, basically, they start to behave unusually. Things happen inside the stars that make them change their sizes over time, and that induces what we call pulsations and unusual eruptions in the stars. And these cause the stars to change in their brightnesses over time. So that is the intrinsic variables. And then you have extrinsic variability, and this is variability caused by external properties, such as eclipses or rotation or star spots. And an interesting fact, a lot of planets around stars are discovered through extrinsic variability because the planets that transit the surface of the star will block some light, and we are able to identify planets because some part of the light of the star is being blocked when this planet comes in front of the star. So that can also happen for stars. So you have systems where there are, let's say, two stars, and one star can come in front of the other, and that will block some light, and we will see that the brightness changes because of that light blocking. And this is such a diverse field. We have roughly 140 different types of variable stars known at the moment. So again, this lends very well for machine learning classification because we want to, classify things into 140 different types. And it's much easier to train a machine to do that than, do it by hand. So here, I've shown an example of a variable in a distant galaxy. You can see how the star changes in brightness over time. So this is the game that you're playing. We're trying to find these kinds of stars across the entire galaxy and classify them. Again, this highlights the complexity of this classification problem. So the variability tree is basically divided into extrinsic variability and intrinsic variability, as I mentioned before. And then you have this huge set of different categories of variables. So the goal is to basically traverse this tree and classify things into each of these categories. And to do that, what we have is called light curves. These are basically time series data sets, and I've shown a few examples from the Assassin survey. On the left, you have a light curve of a variable star, and you can clearly see the brightness is shown in the y-axis, and the time or the date is shown in the x-axis. So there's a clear variation. The star gets brighter and dimmer and so forth. And on the right, you have a constant star, and basically, when you average things out, it basically falls along as a flat line. So the star doesn't do much, and it's not interesting for us to, pursue these constant stars further. And to show the diversity of these stars, here are a few light curves of the different variable star categories that you identify. As you can see, they're very diverse. The shapes of the light curves are very different from one another. And you basically have to design a classifier to tag these stars with these variability types. And that is what I will be talking about in the next few minutes. So the ultimate goal of this project is to systematically identify and classify variable stars using Assassin light curves and a machine learning classifier. And to outline my strategy, so we have these light curves of roughly 100 million stars. And what you can do is to generate features based on these light curves, and including like properties like amplitude and the root mean square value, things like that. Then we run periodograms. These are tools that we use to determine periodicity in the time series data. And then we do the first machine learning step where we identify variable star candidates. we separate variable star candidates from the constant stars, and we don't touch the constant stars here because they're not interesting to what we want to do. And then we also identify duplicate variables because the assassin pixels are somewhat large, and in some parts of the galaxy where there are lots of stars, you can imagine that there'll be, let's say, many stars falling within a pixel, and that will result in duplicate light curves. So we have to deal with that and remove so-called blended variables from our list. And once we have identified candidate variable stars, and after we remove these duplicates, we have to classify these into the different variable types. And that is the second machine learning step. So it is a staggered approach where we first identify variable star candidates and then classify them further. And of course, you should not blindly trust the results of a machine learning classifier. You may have to make sure that the things are as expected. So you do additional sanity checks, and then we end up with a final catalog of these variable stars. So a very interesting part of this project is the search for periods. Most variable stars are periodic, and they have periods ranging from a few hours to years. So this is interesting. Like stars, their brightness changes over a few hours, and we are able to identify that with our data. And in addition to that, there are other stars that change in their brightness over many years, and we are also able to see that kind of variability in the assassin data. And a periodogram that we run is something called the general Lomskagel periodogram and the box least squares periodogram. So we use two different approach because as you can see from the previous light curves I showed you, there are different shapes, and you need to fit a function to the data to identify the periodicity. And for some light curves, sinusoidal fit, basically a sine wave, is a good tool to get the period. But for some light curves where you have eclipses, then you need to have a different approach. So we basically developed two different tools to find the periods of these stars. And I will explain this with an output of what a periodogram looks like. So the periodogram basically calculates the power at a basic frequency or a period. And the best period for a light curve is the one that has the highest power in the periodogram. So on the top, we have the periodogram for a periodic star that varies over 12 hours. And the highest peak in this so-called periodogram is this peak right here, where I've highlighted with an arrow. And we can easily pick that point out and identify the period of the star. So you run these kind of periodograms for millions and millions of stars and find their periods. And that's a very computationally expensive task. So you need to have a lot of tools and a lot of computational power to do that. Okay, then we go to our first machine learning step, where we identify variable stars. And to do that, I've used a random forest classifier for kind of two reasons. It's very easy to implement, and it's very computationally efficient. You can run this kind of classifier on millions and millions of light curves in the order of a few days. So you have to imagine, we have, in this particular part of the project, I've done 60 million light curves, and there are 10 billion data points when you combine all the 60 million light curves. And there's a lot of data that needs to be processed. So you have to be very computationally efficient because you don't have a lot of time on the computers and the servers. So again, in this first step, we just try to separate constant stars from the variable stars. As I mentioned before, only a few % of all stars are variable. So roughly 98% of the stars will be constant stars. So we don't want to waste time on classifying these sources. So we separate these out, and we identify interesting candidates that could be variables. As the features for classification, which is very important, you have to have good features that improve the accuracy and the precision of the classification process. we have periodicity features, and then we have so-called colors of the stars that are basically a proxy for the temperatures of the stars. And we use data from our light curves. And then again, we remove the duplicate sources and we identify candidate variables. So at this stage, let's say we had 60 million in the beginning. We would have roughly 5 million variable star candidates after we run the classifier. So 5 million is still a lot. And again, that is dominated by a lot of false positives. So we had to be careful. To improve the accuracy and the efficiency of our classification, what I did is to use a trove of external data. So Assassin monitors the sky in the optical range, but there have been other surveys that have monitored the sky in, let's say, the infrared or the UV, and they have been mostly done from space. So, and the data is made public, so we can cross-match the Assassin data with data from other surveys. Like, for example, these surveys are shown here: Gaia, WISE, and TUMAS. So we cross-match these data sets, and we are able to get external information, additional information on these stars, and that we can use to improve our classification process. This is important because stars are very complex. To get the best results, you need to have as much information as possible. Again, Assassin only monitors the stars in the optical wavelength range, but there are other surveys that monitor the sky in the infrared and the UV, and that gives us external data. For example, if you have data from, let's say, the optical and the infrared, we are able to generate something called a color, as I mentioned before, which is a proxy for the temperatures of these stars. And that allows us to generate a feature that we can use in our machine learning classifier. And another revolutionary survey is this survey called Gaia, where they basically looked at 1.8 billion stars in the Milky Way to extremely high precisions, and they were able to derive distances to roughly a billion stars, which is very impressive because prior to Gaia, there were only 100,000 stars that had distances, but this survey was a game changer. And knowing the distances to stars, we are able to separate out dwarf stars and giant stars. And that, again, is very useful when we have to basically separate these variable star candidates into the multiple different variable star categories. And this is the next step. So we do a random forest variable classification on the candidate variable stars. And to improve the accuracy, we only consider 8 major variable groups here. And each of these groups can be subdivided into many, many different categories. And to do the subdivision, you don't necessarily need machine learning, but we do need machine learning to divide these into these 8 major groups. And on this figure, I've shown the brightnesses of the stars on the y-axis and the period, the variability period of the stars on the x-axis. So the stars on the left in the pink here, they vary over a few hours, like 3 or 4 hours. And the stars on the right in red and orange, they vary over years. So there's a huge dynamic range in the period of these variable stars. So for features in this machine learning classification, again, we use periodicity. We use the colors that I mentioned before, and we use a lot of light curve characteristics that we can fit models to the shape of the light curve and generate information that we can use to identify the different variable stars. And we really exploit the synergies that we had with other external sources of data, like the distances from Gaia. And we do this, and to make sure that we have a very clean and very reliable catalog, we need to identify and remove false positives. And these false positives are caused by systematics and spurious variability signals in our data. And this is a problem that a lot of observational astronomers had to deal with, because we're dealing with real data, and real data is very messy. And you need to know how to remove false positives and clean our data set. So we do additional checks on this based on their periods, their colors, basic astrophysical relationships, and their brightnesses. And we clean things out, and we come up with a clean, reliable list of variable stars. And we have a final catalog. So what we have done here is to systematically characterize over 61 million stars in the Milky Way. After false positives are removed, we have a catalog of 426,000 variable stars left. And the most exciting part of this is that 220,000 of these stars were new discoveries. So this is really important because, as I mentioned, variable stars have very, very diverse uses in astrophysics. And to use this for such purposes, we need to have a very complete catalog of stars across the Milky Way. And the contribution from what I have done is that we have basically almost increased the number of variable stars in the brightness range accessible to the Assassin survey by roughly 106% increase. And we have identified thousands and thousands of new variable stars, and they have been used for a lot of exciting things, which I will talk to you in a few seconds. So why this catalog is useful is that it's all sky. We have surveyed the entire sky from the northern hemisphere and the southern hemisphere. So we have data for stars from, the North Pole, the South Pole. So it's completely unbiased, and it is classified homogeneously. So this kind of catalog can be used as a training set for future time domain surveys. And the catalog is publicly accessible by anyone. It's available online following this link right here. Okay, to highlight the new variable stars, I've shown a map of the new discoveries that we've identified from the Assassin survey. This is a map of the entire sky. And this ring-like structure that you see is actually the disk of the Milky Way galaxy. And it's really cool that this pops out in our data because most stars are located along the disk of the Milky Way. So the variable stars will also be concentrated along the Milky Way galaxy, and that is what we see here. The cluster of points at the very bottom here are the Magellanic Clouds, and the bigger one is a large Magellanic Cloud, which I talked about earlier. So we can identify variable stars in dwarf galaxies that are like 158,000 light years far away from us as well. So what can this catalog be used for? And this is something that I've explored in my research as well. We've used this catalog to look at the structure of the Milky Way, to look at a category of stars called pulsating stars, where the stars are unstable and they expand and contract over a few hours to a few days. And we've also used this catalog to study eclipsing binary stars, where you have two or more stars in a system, and these can be used to study, as I said before, the radius and the mass of the individual components. And another exciting use is that we can use variable stars to study the chemical abundances of dying stars. So you can look at, let's say, how much carbon or nitrogen or oxygen is there in the atmospheres of these dying stars. And that tells us a lot about how the galaxy is enriched with elements. And another use is that we've used these to study rapidly rotating stars that have star spots. So these are a few examples of what we've used of catalog so far. Another interesting approach is to identify outliers in our data. This is another interesting avenue in machine learning research to identify anomalies and outliers in the data set. And we identified this so-called heartbeat star in the Assassin data. And this is one of the most extreme heartbeat stars ever known. And this is located in the Large Magellanic Cloud at a distance of 158,000 light years away. So I will end this talk by showing an example of what a heartbeat star looks like. So this is data from the NASA test satellite that I've used for the heartbeat star. And here I've shown an ECG diagram and to explain why these stars are called heartbeat stars. So you can see that the shape of the light curve here looks very similar to what an ECG looks like. And that basically gave the way for the classification as heartbeat stars. And this is the most extreme heartbeat star system ever known. And this is a figure from a paper I'm writing right now. But it's very exciting because this is the first heartbeat star in the Large Magellanic Cloud. And we have such beautiful data from the NASA test satellite that we are able to identify what's going on inside these stars in exquisite detail. But this is something for later. In summary, we've systematically characterized the variability of over 61 million Milky Way stars using machine learning and big data techniques. And we've identified 219,000 new variable stars. And we also identified new astrophysical insights from our data. Regarding my upcoming plans, we are working on a citizen science project to crowdsource this classification of 100 million stars in Assassin. So please stay tuned for that. And another project that I'm very excited about is that I'm searching for black holes and neutron stars around Milky Way stars. And we can do that again using the techniques of time domain astronomy. But this is a much more difficult problem because Milky Way black holes and neutron stars are very rare. It's like finding a needle in a haystack. So far, the data I'm getting is basically, we have a lot of false positives, but we've identified one black hole out of a few tens of them. So again, please stay tuned for that. We're trying to find as many black holes and neutron stars around other stars in the galaxy. And with that, I will end my talk. I want to thank the IEEE Young Professional Sri Lanka for inviting me to give this talk. And thank you all for your time and for listening to this talk. Thank you.
Yes, thank you very much for your insightful talk. With that, let's move on to the Q&A session. The first question for you is that, can we complete this degree in Sri Lanka?
So thanks for the question. To repeat, the question was, can we complete a degree in Sri Lanka? I would say it will be very difficult, partially because we don't have a lot of astronomers in Sri Lanka with the accessibility to telescopes. And that's something I think we need to fix in this country. We need to have a national observatory that is up to modern standards. It's a difficult proposition in modern times when you're all, financially worried about the economy. But to really engage young minds in Sri Lanka, it would be a very useful investment to have a telescope, a national observatory in Sri Lanka that is up to modern standards, so we can engage in astronomy research from Sri Lanka itself. Right now, if you want to really pursue a career in astronomy, you are forced to go out of the country, go to the USA, Europe, or Canada, or Australia. So I would say it will be very hard to complete a degree in Sri Lanka. You would have to get a program somewhere else. But we need to change this. That is my opinion.
Yes, and something to think about as well in the future to make a change. So next question is that, what are the types of latest machine learning?
Okay, that's a good question. So in the field that I'm working on, variable stars, the go-to machine learning tool is random forest classification. But people have also been looking at convolutional neural networks, CNNs, to do image processing and to classify astronomical images. But that particular machine learning tool, CNNs, are much more popular in other fields of astrophysics. In particular, they've been used to study galaxies and do cosmology, study gravitational lenses. So machine learning techniques are slowly dribbling into astronomy. It's a little slow because astronomers work with, physics and so forth. So they have to really branch out and study machine learning techniques. But the field is moving towards using machine learning in pretty much everything we do. And people who have very good experience with machine learning will find it very exciting to work in this field, particularly because there's a lot of data coming in. There's so much data to analyze. And if you know machine learning, I think you have a very good start already.
All right. And we've got one more question for you. Is our sun a variable star?
That is an excellent question. So the question was, is our sun a variable star? Again, to define variability, we are basically bound by the limits of our detectors. So assassin telescopes cannot detect tiny variations. And the sun is, if you think about it, like if you go to very, very high precisions, the sun would be a very low level variable star, because you have star spots on the sun that happen over a few cycles, and then that changes the brightness of the sun somewhat more. And you can think about it like, as our sun evolves into a red giant and so forth, it will eventually be a much more prominent variable star. So variable stars do not stay variable all the time. The constant stars evolve into variable stars, and variable stars can evolve back into constant stars. So it's a very dynamic process.
All right. With that, we come to an end of the Q&A session. And thank you so much, Mr. Tharindu Jayasinghe, for this productive session. With that, we come to the end of the fifth session of IEEE Let's Talk BSc to PhD Machine Learning with Physics, organized by the IEEE Young Professionals Sri Lanka. Once again, we would like to extend our gratitude to our guest speaker for today, Mr. Tharindu Jayasinghe, for the insights you shared with us on this topic and your knowledge and your experience. We hope this session was insightful and you all gained a lot from this. We would also like to thank all the participants for their contribution in making this event a success today. We hope you will join us in our future Let's Talk sessions as well. Stay tuned for more information. Thanks again and have a good night.